So we're going to start with number 4 here and then move on to 5. Swimmer in still water swims at this speed. Remember, that's one of the multiple ways they can tell you the speed of the swimmer relative to the water. So they can say in still water, they can say relative to the water, they can say a lot of different ways. Guys, remember, you don't have to work on this one if you don't need it, but just keep the volume low enough so I can hear myself. That would help. He intends to swim directly across the river that has downstream current of this. Okay, so by he intends to swim directly across the river, what they're telling you there is that the final path is going to be across the river. So if I take and this one, I'm going to use a vector diagram for the y. You can go back and forth. You could use words. I don't think in this one it would probably show your understanding that fully using words rather than a diagram. But you can do it either way. So let's. I'm going to draw my river banks this way, and he wants to end up being directly across. So he wants to end up going in that direction. If we say our river flows this way, he's going to have to point upstream so that the river's velocity gets him downstream like that. And let's see, the current is 2.76. So that means this red is 2.76 meters a second. The hit speed is 5.5. 5.51. Yep. Meters per second. And then this would be v of swimmer relative to ground. So that's what I would put for my y, that vector diagram. In my how, I'm going to write it this way, that the velocity of the swimmer relative to the water plus the velocity of the water relative to the ground equals the velocity of the swimmer relative to the ground. That's, I can represent it pictorially or with my vector equation. Now I notice that I have a right triangle, and so they want me to find out the direction from straight across and the velocity relative to the bank. Okay, so they're looking for VSG and theta here. To do theta, I'm going to notice that I have an opposite theta is the red, and the hypotenuse is blue. And the ratio between the opposite and the hypotenuse is sine. So sine of theta equals the opposite, 2.76 meters per second, over the hypotenuse, 5.51 meters per second. So theta is the inverse sine, or the arc sine, depending upon how you say it, 2.76 meters per second over 5.51 meters per second. Plug that into my calculator, making sure that I'm in degrees. And I get 30.1 degrees. See if that comes up. upstream from straight across. Double check my diagram. Yep, that's straight across. So that's upstream from straight across. Check it. Monday morning. And now I need to know the value of that vector, the length of it, the magnitude of it. And so now I'm going to use Pythagoras, where I have a squared plus b squared equals c squared. I have a and c, so I'll rearrange to get b. Well, let's just plug in. I have 2.76 meters per second quantity squared plus b squared equals 5.51 meters per second quantity squared. And I end up with the value of, well, it's not really b anymore. I should have plugged in this is the velocity of the swimmer relative to the ground squared. Sorry. And I would get, most common math mistake here will be forgetting to take the square root of your final answer. But I get 4.77 meters per second. After doing that. Let's see if I can. Okay. Any questions on that one there? Number 4. All right, in number 5, the woman starts to swim directly across the river. I think, in all these, if you can interpret this into a vector diagram, the mathematics after that, it's been stuff that we've been practicing. But it's interpreting sometimes how the question is asked. So she starts to swim directly across the river. That means her velocity relative to the river is going to be directly across. And then it gives you the current downstream. How far downstream will the river carry her by the time she reaches the other side of the river? So in this one, diagram is helpful, but I also think you need some words in this one. I'm going to draw my river and know that she heads directly across. So that's her velocity of the swimmer with respect to the water. This is the velocity of the water with respect to the ground. And then her final velocity will be this direction of the swimmer relative to the ground. But I think in this one, the other understanding that needs to be in here is that the velocity of the water does not change the swimmer's velocity to the water, since they are perpendicular to each other. So because the questions they're asking here is how much time does it take her to cross the river? Well, because she's heading straight across the river, the time to cross the river is going to be the same whether the river's pushing her downstream or the river was not moving, if it was ice or if it was dammed up. It'd still take her the same time to get across the river, because the river's velocity is not changing the rate that she moves across the river. It's just changing the rate she moves down the river, which combined to be the blue vector. So the time A is not going to be affected by whatever the river does. How far downstream will the river carry her by the time she reaches the other side? Well, that's going back to the fact that these two don't affect each other. You could probably write this either way because they're perpendicular to each other. So her green velocity is not going to be affected by the red at all. So it's going to, whatever time she takes to get across the river, she's going to have that much time to move down the river. So I would actually do them completely separately. I'd first look at the across definition, and across, her velocity, her speed is 1.2 meters per second. The distance that she travels, the delta D, is 2,200 meters. Don't even want to forget, don't forget that they gave it to you in kilometers, and so I could also write this as D equals 2,200 meters, D naught equals 0 meters. That's if you're more comfortable with that. And then I would use the equation D equals D naught plus V initial T plus 1/2 AT squared. No acceleration. How can I tell if there was an accelerated, how can I tell from something's path if it's accelerated? If it's moving in 2 dimensions and it's accelerating, what type of path is it going to follow? It's going to be curved, right? It's accelerating and it's going to be curved. Good. So 2,200 meters equals, well, that's 0. So equals 1.2 meters per second times t. T equals, let's see, 1,830 seconds. That's a pretty wide group. Is that right? Oh, wait a minute. I put in 1.2. I had a little dyslexia this morning. That should be 2.1 mathematically. Because it says 2.1 for speed of 2 seconds water, 2.1. I switched it up. So that should give me 1,050. Now I'm paranoid that I didn't get 2,200 right. No, forget it. Let's see if that's right. Yep. Alright. So my answer, of course, is 1047.61904.8 seconds, which rounded to 3 sig figs is that, and that's why I put that into my answer box. But I need to remember that 1,047, or if I'm going to do the second part, which is how far downstream she goes, I know that that's the amount of time I'm going to travel for. The current carries are downstream at 0.91. So this is down slash upstream now, rather than across. And my velocity is 0.91 meters per second. My time is that. And I'm going to use my same equation of d equals d naught plus the initial t plus 1/2 at squared. Nicely, no acceleration. Say she started at 0. So I can use my 0.91 meters per second and then put in my time of 1. Get an answer of 953 meters. Here's how I did. Yay. We're going to go with number 1 here. Each has this. Each flight does when they're initially this part. How much time do the pilots have to take immediate action? So, how many different frames of reference do we have in this one? How many different frames of reference do we have in this problem? Anybody? Great. We can take it from either plane. We can call it, let's call it plane A and plane B, or the Earth. Right? Which one do you prefer we do it from? The Earth? Okay. Okay. So, problem number 1, we're going to go with Earth frame of reference. And for the Earth's frame of reference, let's see, we've got this one's moving this way from the Earth's frame of reference at 685 kilometers an hour. And this one's moving this way at 685 kilometers an hour. And they are 11 kilometers apart. So from the Earth frame of reference, they will meet in the middle. Right? Now, if we had taken it from, say, the left-hand plane's frame of reference, it would have been stationary, and the other plane would have moved towards it, and the Earth would have moved towards it. But in this one, since the Earth is stationary, these two we're going to see come together and meet in the middle. And I think that's part of the key understanding here. So, taking that into consideration, I'm just going to focus in on the left-hand plane, and I know I'm going to call where the left-hand plane starts 0. So that means its d naught is going to be 0 kilometers. Its d is going to be 11 kilometers over 2, because it's going to meet halfway in between. And then I don't know the time, but I know it's not accelerating, so I'm going to stick with my base equation. No acceleration. We called that 0, so that can go away. I have 11 over 2 kilometers equals 685 kilometers multiplied by time. And so I get a time of, let's see, they wanted it seconds, okay. I get a time of 0.00802919171 hours. I'm going to convert that to seconds. Get from hours, see, hours to minute is times 60. Minutes to seconds is times 60 again. And I get 28.9 seconds. Let's see if that works out. 28.9. Yay. All right, so number 6, again, we have 3 different frames of reference. We could look at it from the pirates' frame of reference, the space's frame of reference, or the police's frame of reference. Which one do you want to look at it from? Up to you. Up to the consensus. I know it's a hard decision. From the pirates' frame of reference? You got it. All right. So from the pirates' frame of reference, they're standing still, and and space is moving to the left, and the police are moving to the right. So this is number 6. So we'll do pirates' frame of reference. Pirates are still. Space moves left. Police move right. And probably good to have it. This would probably have been good to have in number 1 also. All velocities are based on frame of reference. And I'm going to do a little diagram here. Let's see. I can't. Well, maybe I should grab their diagram. That could be helpful. Alright, so putting in the things I know. Pirates are traveling. There's traveling. Now, both of these are from the frame of reference of the Earth, right? Or the space. So, if we're doing it in the frame of reference of a pirate, he's not moving, but space, velocity of space with respect to the pirate is that way. So let's see. And then Yeah, that's the only thing I would really change in our diagram there. Now let's record some of our values here. Need to be need to get these right. Let's see. Velocity of the pirate with respect to space equals the velocity of the police with respect to space equals pirate to space is 1143 for me. That kilometers an hour. Velocity of the police with respect to space 1297. Separation is 50 kilometers. All right. If the which way do you want to call positive? I look over here because you guys asked for it. What? Which way? To the right? Okay, so we'll call it to the right positive. So both of these are positive. We need, since we're in the frame of reference of the pirate, we need the velocity of space to the pirate, which would be negative 1143 kilometers an hour. Because if the pirate, if velocity is, we can swap that around, but it's got to change the direction. But now we need to find the velocity of the police to the pirates. We need that in that frame of reference. So what I'm going to add together to find that is the velocity of the police with respect to space plus the velocity of space with respect to the pirates. That will equal the velocity of the police to the pirates. So what I'm doing is I'm translating from the space frame of reference to the pirates frame of reference. All right. So velocity of pirates, police to space is 1297 kilometers an hour. Nicely, these are in one dimension, so the math is easy, right? It's the only difference. Space to pirates plus negative 1143 kilometers an hour. That's the velocity of the police with respect to the pirates. Monday morning, I better use my calculator even though I should be able to do that in my head. 154 kilometers an hour is the velocity of the police with respect to the pirates. So now I know I can look at how far from the pirates frame of reference, that's how fast the police are moving towards them, and they have to go that 50 kilometers. So I'm going to D equals D naught plus V initial T plus 1/2 AT squared. No accelerations here. Say they start at 0, they have to go 50 kilometers at 154 kilometers an hour. And so that takes them 0.3246753 hours. But they wanted to know it in minutes. Well, multiply by 60 to get hours to minutes, and mine comes out to 19.5 minutes, which means they don't get away. So let's see if that's right. I'm going to say no. Kind of my key here is to get it into whatever frame of reference I need it in, get my velocity of what I'm looking at in that frame of reference, and go with that. I like that you chose the pirates, because we don't care how much space is moving, just the chip relative to the pirates. If we'd done it in the frame of reference of the space, yeah, we wouldn't have had to combine any velocities, but we would have had to do double the math work. We would have to figure out, okay, when the police have gone 50 kilometers more than the pirates, how much time did that take? In the pirates, one is stationary, you just have to figure out how long it takes the other one to get there in that frame of reference.